Hey guys, this is 13.7. This is our last video dealing with kinetics and equilibrium, and it's dealing with entropy. All right, so one question to kind of ask is, all these things that we've talked about, physical reactions, chemical reactions, why do chemical and physical changes actually occur? All right, and it all comes back to this topic known as entropy. So entropy, guys, the symbol for it is S, delta S. Remember, guys, delta just means change in something, whether it's delta T or delta H. It's just the change in that substance or in that quantity. All right, so this S means entropy, which is the degree of randomness. All right, so really one word can define what entropy is. So randomness, or chaos, or disorder, or messiness. You guys would know nothing about messiness, am I right? So it's talking about that disorder or chaos in a system. So nature tends to proceed to a state of lower entropy. I'm sorry, nope, wrong, completely wrong. I was thinking of something else. I was thinking of energy, duh, brain fart. Greater entropy, okay, or disorder. Now the example that I use for this is, one, my desk. Beginning of the school year, my desk is pretty clean, it's organized, but as the year goes on, more and more stuff piles up. It gets messier and messier. I'll be honest, I know where everything is, but it doesn't look great. Another example might be your bedroom. All right, so you can put all the time and effort you want into cleaning it, but over time, what tends to happen? Now, if we're being honest with ourselves, it does not stay clean. Now, you might be thinking, well, yeah, mine's always clean, but let's put it this way. Another way to think about it, how much energy and time do you have to put in to keeping your room clean and organized? If you just let it go by itself and not put any extra effort into it, it's going to go toward chaos and disorder. Every system in the world, in the universe, goes toward disorder and chaos, not order. It takes a lot of energy and a lot of intentionality to keep things in order. All right, and that's what this is all dealing with. So the more order you have, okay, the less entropy is in your system. Okay, so the more organized something is, the less entropy. So again, remember, entropy just is chaos and randomness. The less order you have, the more entropy that is in your system. Okay, so there's one thing that within a reaction that we're going to look at to really tell us what's going on with delta S, and that would be your phases, okay, or the phase change piece. Excuse me. It's the most significant factor in determining our delta S. Okay, and how we can show that here in a second is with pictures. So as I go from a solid to a liquid to aqueous to gas, my entropy is increasing. Okay, so as you go from a solid to a gas, your entropy is increasing. Again, just think about it, guys, at the particle level. We've talked about with KMT already this year. What does a solid look like? We've drawn particle diagrams for all four states already. What does a solid look like? Are the particles scattered or are they close together? They're very, very close together, very compact, very neat and organized, very, very rigid. That's not a lot of disorder. That's very fine-tuned, and it's very meticulous with how they're put together. When we kind of progress then, I'm going to write low delta S, high delta S. All right, liquids then, if we draw our liquid line in, now what happens to the particles? They get more spread out, right? More further apart. So now, oh wait, there's more chaos, more randomness. I want a thing there, I want something here. It's not really organized. All right, they start to spread out. The further away particles get, the more chaos there is. All right, aqueous. Anybody thinking, how is that different than solid, or excuse me, not solids, liquids? Well, we still have like our water particles, but now we also have ions in there, guys. And now once you introduce that, then you have more randomness because you don't know where those ions are going to be. But there's still not as great entropy as gases, because gases are going crazy. They're bouncing off the walls. They're going in any random direction. They're all over the place. They might even break out of the container. Okay, so keep it simple when we're dealing with entropy. You're only looking at the states of matter. And you guys, we've studied states of matter already, so this should be somewhat of a review in terms of how the particles are behaving. Okay, so entropy increases when a compound is broken down. Okay, when you split those bonds, right, they're together, and as soon as you break them apart, you have more particles. So the more particles you have can also mean something about entropy. Okay, so here we had 1 when they're bonded together. Now we have 2. That's more chaos. They can go and they can move on their own. Excuse me. Entropy decreases when a compound is created and bonds are formed. Right? So, note right here, if there's no phase change, count up the number of molecules on each side, so the number of moles. The lower number of moles means that the entropy is lower, which means you have a negative delta S. If the moles are increasing or greater, that means your entropy is greater and you have a positive delta S. All right? So those are our notes and stuff for it. Let's go into some practice examples together. I'm going to kind of do and explain the first few. Then I want you guys to pause it, go through them, and then come back and check your answers. So number 1, again, all we're looking at here, guys, within these reactions are the states of matter. So on the left, I only have solids. On the right, I have a solid as well, but I also have a gas. So right away, seeing gas, my entropy is going to increase. More disordered, more chaos. Number 2, I've got a liquid on the left and a solid on the right. So what's happening? Well, liquid is the particles are spread out farther, so there's more chaos and order. They're coming together and getting closer. Less chaos, less randomness, so our entropy is going to decrease. All right. Number 3, the last one we're going to do together right here, then I want you guys to try them on your own. They're all gases. All right, so if they're all the same substance, now we have to go to the secondary factor, and that's counting up the number of moles. So I have 1 plus 3, I have 4 moles on the left, I have 2 on the right. So which one has less? Or I'm sorry, as you go from left to right, what's happening? Well, we go from 4 to 2, that's less. That means our entropy is decreasing, means it's getting less and less chaotic. All right, so pause the video. I want you guys to try to finish these last few problems here and then come back and check your answers. All right, number 4, I'm going to move a little bit quicker. So if you're confused still, guys, call me over, pause the video, stop. Don't just go through and watch this. Let's have a conversation in person and make sure you understand it. We can go through a couple more together in person. Number 4, entropy is increasing. Solid to aqueous, increasing. Number 5, solid to liquid, increasing. Number 6, solid to gas, increasing. Number 7, aqueous to liquid, decreasing. Solid and gas to only gas, increasing. Because again, you had some order here with solids. Now it's all gases, so it's definitely increasing. Number 9, they're all gases. So 2 on the left, 2 on the right, no change. All right, it's constant. There's no entropy change there because it's the same amount on both sides. Well, actually, the more I think about it, guys, think about this, right? You have 2 separate species here, and you have 1 species on the right. Technically, your entropy is decreasing because they're creating bonds. So, I'm sorry, my initial answer was incorrect. This is decreasing. So my answer key is also incorrect. I went through it too fast before. All right, number 10, aqueous to solid, decreasing. 11, we're going from 2 moles of gas, so 2, and then you have 3, so that's increasing. You're also breaking apart, so you're creating 2 substances versus 1. 12, we have all solids on the left, but again, 2 different substances. Now you're going to 1, so that's going to decrease. 13, aqueous to liquid is decreasing. 14, you have 2 moles of gas. You have 2 moles on the right, but again, you have 1 substance on the left, 2 on the right. Your entropy is going to increase. And number 15, gas to solid would be decreasing. So, you guys have this last practice sheet. I have more in the binder as well. Any questions about anything, make sure you ask. I'll see you guys in the next unit.